Good morning.
Morning, sir.
Morning. See, I'll open a poll. This is regarding the time that you need to complete the course that I had asked you. Uh, you had to just pick the option that I have given. Uh, okay. Are you able to see the poll? Yes, I think people have started it. Okay. So in the last class, we were discussing about enhancement technique, particularly piecewise linear transformation was initiated. In fact, I started explaining it. Okay, so are you able to see my slide? Piecewise linear transformation.
Yes, sir.
Okay, fine. So what we understood is, uh, suppose if I have maybe a transformation function which doesn't have a simple equation to represent it. So I need to go for approximating any such nonlinear transformation by using piecewise linear functions. In the last class, I explained about it. So you can just observe here. This is a linear graph, but not completely linear. That means the slope is not constant all through. Only in this portion, in this piece, the slope is constant. Again, in this piece, the slope is constant. So we call this as piecewise linear transformation function. And what is done here is, just to give an example, suppose if I have a low contrast image like this, and if I am interested in probably some dots that are seen on this, okay, probably for some requirement, you cannot use simple thresholding technique to separate it because most of the gray level values are same. So what they do is they'll just try to, okay, separate the difference between the dark pixel and the white pixel by using this type of contrast stretching transformation. So what you would observe here is these values from 0 to this value, they are actually slightly reduced to darker side, and these values are made white. So thereby the difference between the dark pixels and the white pixel increase. You can observe that compared to this, I could see these dark pixels and also the white pixels. Now when I put a threshold on this simple thresholding technique, that means anything above some level is white, below that level is black, you will get a binary image of this nature. So whatever that you would like to see from these dots, now I could separate it directly, easily. This is the advantage of piecewise linear transformations. There are some typical examples of these things. For example, in this case, assume that I am interested in highlighting a specific range of gray levels. What do I mean by that? For example, in a satellite image, let us assume that the vegetation region or maybe the forest region takes some gray levels in fact gray shade image, maybe some values say from 100 to 150, and I am interested in only identifying the green region or vegetation region from a satellite image. So what I can do is I can use this type of simple technique. Just observe from A to B, input gray levels from A to B. I'll I'll just enhance them, and 0 to A and B to L minus 1. I'll just try to put them towards the darker side. So only A to B, which is of my interest, is enhanced. So for example, if A is 100 and B is 150, which may be the range of pixels, when I convert a satellite image, color satellite image into gray shade, and this range of pixels is for vegetation region. Let us assume that. So only that vegetation region is enhanced. So the rest of the things I am not interested in. So a specific range of gray levels I can enhance. This is the first one. The second one is slightly different. Of course, from A to B it is enhanced, but I don't want to compress. That means don't want to make them dark. I want to retain them as it is. So you can see that this is a 45-degree line. The meaning of a 45-degree line means whatever is the input gray level, the output gray level will be same. So I'll retain the background, only the point of interest, my interesting region, I'll just enhance it. For example, satellite images, vegetation region I'll enhance, but the rest of the region I'll keep them as it is. I'll not disturb them. So that is a second transformation function. And what you are trying to do here is you can just see 0 to L minus 1 is the input gray level. So I have just taken different slice of it. 0 to A is one slice, A to B is another slice, and B to L minus 1 is the third slice. So I am just dividing the gray level into different pieces or slices and enhancing it. That is why the name gray level slicing. You are just slicing the input gray level into different ranges and then taking a decision based on the slice of your interest. Okay. Now what you see is an example. Hope on your small screen it is visible. This is actually in fact, this is a road. I don't know how good it is on your screen. And this is actually a car. So in this case, when I just use a simple transformation function that highlights a specific range, okay, uh, this is what you get. So carefully observe, I am interested only in this region. The rest of the region, I want to make it dark. So you can observe that the rest of the region is made dark. Only this region is enhanced. So this is very important whenever you are interested in a specific range of pixels in an image. Okay, this is called gray level slicing because the gray level is sliced to different ranges and decision is taken. Another good example here is an angiogram image. What is done here is figure 3.118, that is this type of transformation is taken and you are enhancing it. So carefully observe, I am interested only in some portion of this region and the rest of the region I am not interested in. So actually in this case what is done is the upper gray level scale values are enhanced. So you can observe that mostly those pixels which are looking white are towards whiter side, that is enhanced, whereas the remaining region is darkened. So you are using something like this. Only thing is this A to B is shifted towards the higher side. That means probably from the higher range of pixels, maybe from 200 to 255, I'll just enhance it. That's what has happened. And in this case, what is that you are observing here is you are using this type of uh, transformation function. So the background is kept as it is, only the required region is enhanced. That's what you see here. So the required region is enhanced, but you can see that the background is kept as it is. So you are not going to disturb the other regions here. So as you can see. Okay. So this is about gray level slicing. There is another type of slicing technique called bit plane slicing. Now to explain this, probably I have to go to my OneNote. Let me just close the video and go to OneNote. Okay, so is my OneNote screen visible?
Yes, sir.
Okay. So what you should see is here. Let me just take an example image. Then it would be easy for you. So I'll just take an example image. Maybe for my uh, requirement, I'll just take a 4-bit image. A 4-bit 4 cross 4 image. So can somebody tell me if it is a 4-bit 4 cross 4 image, what are the gray levels you will have? What is the range of gray levels I can have for a 4-bit image? 0 to 4-bit image. Can somebody
15.
else? Correct. So 4-bit image, I can expect the gray level values in the range 0 to 15. So I'll just take typically some values. So I'll write it in. Okay, so for example, let this be 12, let this be 10, 11, let this be 8, this is 9, 0, 5. Some values I'm just taking. Some values. I think some of them are missing, it's okay. So now you all know that this I can represent each of them by using 4 bits. For example, 0 is represented as 000, 1 is represented as 0001. This is very simple uh, Boolean algebra that you have already discussed. So I'll not write all of them. So 15 is represented as 1111. So this is bit 0 and this is bit 1 and this is bit 2, this is bit 3, like this, depending on the number of bits I am using. So in this case I am using 4 bits. B 0 is the least significant bit. This is the least significant bit and B3 is the most significant bit. These are simple things that you have already studied. Okay, so now uh, each of this bit, it has some significance on the representation of the image. All of you know about it. For example, suppose if I have 1011, so this has a weight equal to 1 and this has a weight equal to 2, this has a weight equal to uh, 4 and this has a weight equal to 8. So this is what you know. So equivalent value is 8 plus 2, so 11. Now in such a case, for some reason, suppose if I just make this bit equal to 0, so the value that I'll get is 1010 and it is 10. Now all of you know that in terms of the image, if I look at 11 as a gray shade and 10 as a gray shade, you will hardly have any difference. Both of them look dark to you. I hope you are understanding what I meant here. So the significance of this on the image is very less. So what we do in bit plane slicing is the following. Okay, so we will produce several planes of this image and try to show it as an image. So let me just tell you how I'll take bit 0. So I just want to know what is the significance of bit 0 on the image. So what I will do is I'll just generate another image, okay, by keeping bit 0 b naught as it is and masking other values. What do I mean? Other bits. That means b1, b2, b3, I'll make them as 0. And then write an equivalent decimal value in the matrix. So all of you know 12 means, I'll just take few examples. The rest I think you can directly tell me. So 12 is, all of you know, it is 100, correct? So now I have to mask all these bits and retain only this bit. So what happens? I'll get 0000. So 12 is 0000. That means I am masking the higher bits and retaining only bit 0. Okay. The equivalent of this is 0. So 12 will become 0. Now can somebody tell me what will happen to 11 with this logic? 11 is 1011. So you have to retain this and mask the rest of the bits. What will happen? Is this correct? Hello?
Yes, sir.
Okay, so 11 will become 1. Then what will be 8? Now somebody quickly tell me what will happen to 8? 8
Zero,
will,
zero, zero,
correct.
zero.
8 is 0 finally after masking, I am telling. So 8 is 0, 9 will become 1. 0 will continue as 0, 5 will become 1, 6 will become 0, 7 will become 1, 10 is 0, 11 is 1, 12 is 0, 15 is 1, this is 0, this is 0, this is 1, this is 0. So your output image, when I mask all the higher bits and retain bit 0, is this. Okay, this is called one of the that means bit plane 0. This is called bit plane 0. That means retaining the 0th bit and masking the other bits. Is the point clear? Is the point clear? What I have done from here to here? Somebody respond.
Yes.
Okay. Now let us see how I'll generate bit plane 1. Again the procedure is same. I'll mask bit, sorry, I'll retain bit plane 1, sorry, the bit 1, and mask other bits. Okay, again I'll take the example. First pixel is 12, so I'll take the example of 12 and write it as binary, so it is 1100. Now what you have to do is you have to retain this and mask all of them. That means make these 3 bits zeros, retain this bit. So since that bit is a 0 here, it will be 0000 only. So the output will be 0. So you will again get this bit as 0. The next one is 11. So let me just take that 11. 11 is 1011. Now you have to retain this bit and mask the other bits. So other bits are zeros. This bit is 1, this is 0. The equivalent of this, all of you know, is 2. Okay. The next one is 8. So 8 is 1100. I have to retain this bit. Other bits I should mask. So if I retain that bit, it is 0. So 8 will become 0. Now with this logic, I want you to tell the other bits. Okay. So this is 2. This is 0. What will be 9? Can somebody tell me? What will happen to 9? What will be the output here? Quickly. Should not be difficult. What is 9 at least in binary? Please respond. Don't keep
Zero,
quiet. Yeah, it will be 0 because 9 is 1001. You have to retain this bit. Other bit should be masked. So the output will be 000. Very good. Okay. So then what about 0 will continue to be 0. 5 will be 2. 6 will be 0. 7 will be 2. 10 will be 2. 11 is 2. 12 is 0. 15 is 2. 4 is 0. 2 continues to be 2. 1 will be 0. 0 will be 0. Any doubt in writing bit plane 1?
no, sir.
Okay. So this is how I write bit plane 1. Now I'll write bit plane 2. Again the same procedure. You have to retain second bit and mask the other bits. So let me just explain it here only. For example, 12 is 1100. I have to retain this bit now and mask the other bit. So it is 0100. This is 4. 11 is 1011. You have to retain this bit and mask the other bit. So this will be 0000. So this will be 0. The next one is 8. 8 is 1000. You have to retain this bit and mask the other bits. This will become 00. Therefore, this is 0. So like this, if I write 12 will become 4. 11 is 0. 8 is also 0. What is the next one? The next one is 9. So can somebody tell me what happens to 9? What happens to 9? Any doubt or you don't want to comment? Is it correct?
Yes.
Okay. Now what are the other bits? 0 continues to be 0. What will happen to 5? 5? 5
Sir,
will be, yeah, please.
sir, sir, in B2, The 5 will be 0, right, sir?
P1 planes.
Wait a
Sir,
minute, wait a minute.
please.
What is the doubt? Please. In B to 5, 5 you want to write, right? 5 is 0, 1,
In
0,
the
1, no? Correct, no?
sir, in B1, sir, sorry.
In B1 planes.
Okay, in B1, uh, 0, 1, 0, 1. Okay, okay. I have written it as 2. Sorry, I think this
Yes.
is wrong. Correct. Thanks. Thank you. So you understood. That's all is required.
And
Yeah.
and
Any
sir,
other
the
doubt
Sir,
I have done?
binary
sir,
form of 8, sir.
Pardon?
Binary form of 8.
Okay.
That is uh, 0, 1, 0, 0 should be there.
Oh, sorry,
Binary
sorry.
form.
Okay, okay, I have written it
So
wrongly, but I
anyway,
think the answer
yes,
is
yes.
correct. Okay,
Yes, sir. Yes, sir.
correct, correct. So is this correct now? I think you have understood all of you. So that is what is required to me. If I made such simple mistakes, it's okay, manage it. So 6 means it is 0, 1, 1, 0. So it will be 4. So you know what is happening. Carefully observe what is happening. In this case, all odd values will become 1, all even values will become 0. In this case, all the values in the second case, all the values which have the second bit 0, they will become 0, whereas all the values where the b1 bit is 1, they will become 2. So, you know, in bit plane 0, I'll have 0 and 1. In bit plane 1, I'll have 0 and 2. In bit plane 3, I'll have 4 and 0. And finally, I think I want you to complete this since you have understood. The last one is bit plane 3. So here, for example, 12 is 1100. So you have to retain bit plane 3 and mask the other bits. So this will become 1000, which will be 8. So which means either the value will be 8 or a 0. Okay. So what is the next one? 11, I think. So 11 is 1011. You have to retain this bit. So it will become 1000 and this is 8. And so on and so forth. So I want you to complete this matrix also. Okay. I hope the concept is clear. This is called bit plane slicing. Okay. Shall I move to the slide? Is this concept okay?
Yes, sir.
Okay. If there are any such mistakes I have done because of writing it, please correct them. Okay. Anyway, so I think you have understood the concept. That's all is required to me. So whenever I have a 4-bit image, I'll have 4-bit plane. One that is B0, the least significant bit, B1, B2, B3, the most significant bit. So if I have an 8-bit image, I'll have 8 such bit planes. Okay. And all of you know 8-bit plane means uh, you will have 8 bits. So depending on the values, you can have 0, you can have 2, you can have 4, 8, 16, etc. Power of 2. Okay. So that is what is explained in this case. So instead of highlighting the gray level ranges, see here I was highlighting the gray level ranges. Here you are trying to look at the contribution from each of the specific bit and highlight that. That's what we did in our example now. So what we did here is I just took the contribution from the third bit here. The third bit is actually fourth bit. If I start with B0, it is the third bit. Okay. So this is actually the fourth bit in the most significant bit. This is a contribution from the previous one. This is a contribution. So that is exactly what he is trying to say here. And look at the appearance of the image depending on the bit. See, for example, I have bit plane 0 and I have the maximum as bit plane 7. So this will be the most significant bit. This will be the least significant bit. So you are slicing based on the bit value. That means the level of the bit, whether it is 0 or 1, and take a decision based on that. So show the images of all. So I'll have 8 such images. This is an example. I hope all of you can see. This is actually called as a fractal image. More about it, please Google it. Fractal images. What do you mean by that? So you have an image here. and the bit planes are shown here. For example, in this case, I think on the bottom it is given here. So this is the 0th bit plane, this is the first bit plane, second, third, fourth, fifth, sixth and seventh. That means this is the most significant bit, contribution from the most significant bit, contribution from the least significant bit. So any quick observation on these images, what do you notice, which is obvious actually? Can somebody respond? Quick observation on this. What do you notice? Sorry. Nobody want to respond? Anybody? Quick observation compared to this and this, what is it? So, or I'll ask you a different question. Suppose if I give you this image, by any way can you say this is the image, original image? No, you can only see that there is a circular region, but the inside details are missing. Whereas if I am giving you this image, you can definitely say it could be of this type of image. So I can just relate them. Whereas here it is very difficult. Okay, am I clear? Am I clear?
Yes, sir.
Okay. So this is exactly what we were trying to understand. That means what it tells me is the least significant bit carries very little information about the image, whereas the most significant bit carries maximum information about the image. So what that does means is, even if I mask these least significant bits, for example, 0th bit and first bit, if I mask them, my image may not get diverted or deviated too much. That means I can still represent or identify the image. That means some of the bits are not significant. That's what it says. This is another example. This is an 8-bit grayscale image of size 500 cross 1192 pixels, and in fact these are the bit planes. This is bit plane 1, 2, 3, 4, 5, 6, 7, 8. Here he is counting from 1 to 8. That's okay. So you know what is the meaning. So this is the least significant bit, this is the most significant bit. I can read this entire thing and I can say this is the original, whereas here I cannot say that this is actually a currency. Okay, so every bit has got its own significance. Most significant bit will definitely have the higher significance. That means it carries much information about the image. Now what is shown here is this is an image which is reconstructed by using bit plane 8 and 7. That means these two are used and you are reconstructing this. So it's almost looking like original. 876 is used and 87. That means just to know how is it significant. So what it tells me is it's enough I use bit plane 5, 6, 7 and 8 to represent the image. That means the least significant bits doesn't alter much. So this concept will be used in what is known as digital watermarking. Okay, I want one of you to just probably go through this, and I'll be happy if you can quickly explain this in the class as a presentation for about 5 minutes. What do you understand by the term digital watermarking? You can just if you want, I can write it on the. Okay, so it's called digital watermarking. Definitely those of you who are interested in making a presentation, maybe some consideration will be given, but I can only give provision for one student. So digital watermarking. So please look at this. So the concept is used in digital watermarking. Okay. So if somebody explains it in the class, I will be happy. Okay. So you understood what is the meaning of bit plane slicing. Let me just okay, I think demonstration is not required because this is already explaining it. So let me just go to the next concept called histogram processing. This is a very important concept. In fact, there could be problems on this concept also. please understand the concept very clearly. Uh, Let me just explain the concept of histogram processing. I think in at least in some of your probably courses you would have learnt about histogram, but it's a very simple concept where you are converting a two-dimensional image into a one-dimensional image, one-dimensional data. So what we do is, for example, if I have a two-dimensional image like this, is the slide clearly visible? Hello?
Yes, sir.
Okay. So this is an image, and let us assume that there are six gray levels depending on the bits used. I think in this case he is assuming six gray levels. So I can have the values from 1 to 6. In this case, he is not taking 0. It's only an example, so don't worry. So I have six different gray levels. If you carefully observe, gray level 1 has appeared 5 times. So if you count 1, 2, 3, 4 and 5. And gray level 2 is appearing about 4 times. 1, 2, 3 and 4. Similarly, count 3, you will have 5 threes here, 6 fours, 2 fives and 14 6. So if I now plot this as a one-dimensional signal, x-axis will have the gray levels and y-axis will have how many times each of that gray level is repeating. We call this as the histogram. So you have 5 ones, 4 twos, 5 threes and 6 fours, 2 fives and 14 6. Okay, so this is called histogram. This is called histogram of an image. That means for every image, I'll just see how many gray levels are there and count each gray level, how many times it is repeating, and plot it as a one-dimensional plot. Okay. Now then, what is done is next, uh, to normalize these values, I will divide it by the total number of pixels. For example, in this case, I think this is a 6 cross 6 image, which means I'll have 36 pixels. So instead of writing 5, I'll write 5 by 36, 4 by 36, 5 by 36, etc. 6 by 36, 2 by 36 and 14 by 36. So you are counting how many times each of the values appearing and dividing it by the total number of pixels. So loosely speaking, this is probability of occurrence of each of them. Why I say loosely speaking, because you cannot consider it to be a true probability. If you want true probability, actually you should have infinite values. The probability works out only when the number of observations is infinity. All of you know who have done random processes course last semester. Under limiting case, when n tends to infinity, the probability value will be nk by n. So that is why I said loosely speaking. So I can just say 5 by 36 is the probability of occurrence of 1, 4 by 36 is the probability of occurrence of 2, etc. Okay. So which means that I am plotting the probability value versus each of the value. So if you take the x-axis as is a random variable and y-axis as the probability of that random variable, and all of you know that it is called the probability distribution. Okay, so histogram, I can say loosely speaking, is the probability distribution of the various gray levels of the image. I hope this is clear to you. Okay, so now let me take some examples. Okay, what you see on the left hand side is an image. What you see on the right hand side is the histogram of the image. There is a very simple command. I think those of you have completed the course, uh, this command is already known to you. To plot the histogram of a given image, you will use a command HIST. Okay, so what is seen here is histogram of the image. Now you notice that even though you can have gray levels from 0 to 255, most of the gray levels are crowded towards the darker region. So this is a typical histogram of a dark image. Okay, so if I give you this histogram, you can tell me the nature of the image. You can say this is a dark image, but you cannot tell me what is the image, because that is not possible, because it is a conversion from two dimension to one dimension. So inverse is not possible. Given histogram, I cannot get back the original image. Okay, please remember that. In this case, most of the gray levels, as you can see, is towards the brighter side. So this is a bright image. In this case, neither I have dark pixels nor I have bright pixels. So you can call it as a low contrast image. Neither I have dark pixels nor I have bright pixels. Whereas in this case, you can have all the gray levels from 0 to 255 very nicely distributed, and most of them are same. You can observe that it is almost like a uniform distribution. I hope you know what is the meaning of uniform distribution. The probability of occurrence of each of the random value is same. So you among these four, all of you will agree with me that the last image is better. Okay, so I can have any of these type of images. When is it possible? This is possible when probably the light illumination is very less. This is possible when the illumination is too much. And this is also possible when probably it is not uniformly lit in a, for example, in a dark room. Maybe near the windows, there could be some light, whereas away from the windows it may not be too light. So because of that, you may have a very low contrast image. So suppose if these type of images are captured by probably any of the camera, which is not suitable for us, because you can see that all the three are not that good for us. So is there any way, the question is there any way that I can convert an image whose histogram looks like this to an image whose histogram looks like this, because I see that this is better. Okay, so you are now converting an image which is having this type of histogram to an image which is having this type of histogram. Okay, so let me just introduce this in terms of a random variable. Those who did random processes last semester, please concentrate. This is a random variable having an arbitrary histogram like this, or sorry, arbitrary probability density function like this. And this is an image whose histogram, or sorry, whose PDF is uniform. So the question that I am asking is, can I convert a random variable having an arbitrary PDF to another random variable having a specific type of PDF? Okay. Can anybody tell me what was uh, the term that I used? Those of you who attended my class, for this type of conversion from random variable from one type to other type. I think in second chapter we discussed about it. I also probably had mentioned this example there. If you remember, anybody, I'll be happy.
Transformation.
Very good, very good. Who is it?
Sindhu TV, sir.
Sindhu, very good. So this comes under the heading of transformation of a random variable. That means transforming a random variable x having a PDF fx of x into another random variable y having a PDF fy of y. I think it's good that you remember, recollected it. Very good, Sindhu. Fine. So now that is what we are trying to do. Converting an image from one type of PDF to another image with another type of PDF. In terms of histogram, transforming an image with one type of histogram to another type. Because you have no way, you cannot see these type of images will be captured by image. For example, let us assume that I have installed a camera near the traffic signal point. You cannot expect uniform light intensity always. So the image may be captured somewhere in the evening where I would have captured this type of image. So I cannot expect the lights to be on there always. So in that such cases, how do I get an image of this nature? It is by using what is known as histogram equalization. Okay. So since there is not much time, let us not start that new topic. Instead, I'll just see whether I can demonstrate the concepts by using MATLAB. Hope MATLAB is also taking some time. Okay, so let me just see whether I have any. Okay, this is the one. Is the MATLAB window visible? Hello?
Yes, sir.
Okay, so what I'll do is I'll just demonstrate bit plane slicing first. Hope this should work. I have not tested it. I hope I think it will work. So let me just run this. Okay, I think there is some problem. Probably the image is not available. So I'll just try some other image. Okay, so this is a child image. I think there is some issue here. Since I have not checked it earlier. Oh, okay. I think the size of the image is a problem. Anyway, let us not worry about it. So, uh, what I'll do is I'll just try to plot the histogram of this image. Uh, Let me just read the image. So, this is the child image. So, I'll convert it into gray. All of you know how I can convert RGB to gray. This is the command. Okay. Now, I'll just plot the histogram of this image. Hist of x is the command. Uh, why is it not taking? Sorry. Okay, I think I'll just go to my better. Sorry, I didn't check this earlier. So let me just go to my. Okay, so yeah, so here I think I'll demonstrate it. I'll go to histogram. So let me just read maybe cameraman image and plot its histogram. So hopefully you can see the histogram here. So what you would notice here is there are good number of dark pixels, which is very clearly evident in this particular image. There are a good number of images with a gray shade somewhere around 150 to 200. Now carefully observe in this image, nowhere you see completely white pixels, so that is why these values are almost equal to 0. So let us try this for another image. Maybe Lerna is another image, so I'll plot its histogram. So you can see the distribution, it's almost from 0 to 255. Of course, the lower darker side it is not there, higher whiter side it is not there, but most of the pixels are there. So this is how you can plot histogram. The command that I use is hist, H-I-S-T, hist of the image. So there are many, uh, in fact, yeah, I think I can also show you what is equalization, which we will probably mathematically discuss in the next class. So notice that this is a low contrast image. I already gave you an example of low contrast image. Low values, the gray values are in somewhere in the mid region. That is this particular case, this case, third case. So in this case, it is not looking that good because you don't have low or dark higher pixels. So if I just try to convert this into a uniform, that means transform this into a uniform distribution type of image, the image looks better. So this is called histogram equalization. We should discuss mathematically as a concept of transformation of random variable, which we will do it in the next class. Okay, so with this we will close the class.